Our guest, welcome everybody. Our guest speaker is Koushiki Bhattacharyya. She is a PhD student in International Center for Space and Cosmology, Ahmedabad University, India. Her supervisor is Professor Pankaj Joshi. And we see the title, Gravitational Collapse of Scalar Fields, Fundamentals and Applications. So, Koushiki, please begin your talk.
Yes, thank you very much, Professor Piotsky, for uh, introducing me to this wonderful opportunity. So I'll talk about the gravitational collapse of real scalar fields, and the talk is segmented into these three main parts. First, I'll introduce some key concepts. Then I'll talk about the fundamentals of why we discuss about these topics, and then I'll talk about some cosmological applications. So, first of all, it's important to ask what is gravitational collapse. So, if we see in our universe, it has been expanding for a long while, but nevertheless, we can see that there are stable structures like galaxies, stars, and even very important structures like singularities on the star. And uh, we assume or we suspect that all of these objects have occurred because of a fundamental physical process called gravitational collapse. Why does it happen? Let's take a star like the sun. It has an enormous amount of fuel inside it, like fissions and fusions. It has a lot of pressure generated inside it, and the pressure is pushing the surface of the sun outwards, and the gravitational pull of itself is pulling it towards its own center. Let's say that the fuel goes out. So at this very point, the self gravity of a star like sun will make it collapse on itself due to its own self gravity. It can happen to a far massive star than the sun, and then we can have a continual collapse that will give us a singularity. It can also happen to far sparse uh, collapsing clouds like a dust cloud. Then it will give us something like a planet or a galaxy or something else. So, in the study of gravitational collapse, we always contain ourselves within a coordinate frame called the co-moving coordinate system. In this system, the force velocity will be a Dirac delta function, and the physical radius of a collapsing star will be given by the first equation given in this slide. My pointer is unfortunately not working, so I cannot show you using the pointer. But the first equation in the slide shows the relationship between the scale factor, that is the A, small a given in it, to the physical radius of the star. So the physical radius will be decreasing if we are having a collapsing cloud, and the co-moving radius, that is the small r, it will not change. So what happens during a collapse is the physical radius keeps decreasing and decreasing. And if the pressure somehow during the collapse is sufficient enough, the collapse can halt into an equilibrium configuration, which is not a singularity. But if the collapse is violent enough, it can end up in a singularity. We'll talk about all these scenarios. I'll talk about all these scenarios later on. And because the physical radius is decreasing and the co-moving radius is not changing, the scale factor will also be less than 0. And in this case, the time-like congruence is, let's say I am an observer and I'll always move along a time-like geodesic. And in a collapsing scenario, the time-like congruence will always have a expansion scalar given in theta, given as theta in this third equation of this slide. It will always be negative. And in the last figure, what I've shown here is a collapsing cloud. The first circle represents a collapsing cloud. And while the cloud is collapsing on itself, an horizon can start to begin. And afterwards, the whole cloud is enclosed by the horizon. And then we'll have a black hole. But different scenarios can also occur. And I'll talk about those. Now, I'll talk about what the gravitational collapse of scalar fields. So we'll also talk about what is a scalar field. A scalar field is just a map from the manifold, from each point of the manifold to the real line. And because we have to map the functions of the scalar field to some physical observables, we'll also have to have a Lagrangian corresponding to the scalar field. And the Lagrangian of a scalar field with some non-zero potential is given in the second equation of this slide. And if we integrate the first equation, we have the action corresponding to the scalar field. And then by extremizing that, we can get the stress energy tensor of the scalar field, which is given in the third equation. And by taking the third equation, we can actually see the whole dynamics that represents the collapse of a scalar field. Now, why would we be interested in the collapse of a scalar field? So the first motivation is to understand more about the cosmic censorship conjecture. It was given by Penrose in 1965, and later on in 1969. There are two versions of this conjecture. In the stronger one, they say that any singularity is not visible to any observer near or far. That is the strong cosmic censorship conjecture. And the weaker cosmic censorship conjecture tells us that only nearby observers can see the singularity. When I say that nearby observers, I mean both time and space, because in this case, in the realm of GR, local also means an instant in time. So it might be that a singularity is observable to some observer at a single point in space and time. At a later time, the singularity might also enclose itself within a horizon. So Penrose hypothesized it, but yet there are no mathematical concrete proofs of this cosmic censorship conjecture, and hence the question still remains whether it is true or not. We'll try to investigate this. Then comes another very beautiful question, whether a critical phenomena can occur in gravitational collapse. So critical phenomena is what? It's like melting of ice. Ice can melt only at 0 degrees centigrade. Any temperature in and around that cannot melt ice. At exact 0 degrees centigrade will ice melt. And this kind of a phenomena can also be observed when we see the collapse of a massless scalar field. It was observed by Chopwick, and I'll talk about this as well. And there comes the applications in cosmology. So the first thing there is the dark matter. Axionic dark matter is hypothesized to be driven by scalar fields. Then there are multiple theories of dark energy, multiple potentials of dark energy that are also motivated by scalar fields. And there is also the question of structure formation. There are multiple studies where the dark energy component is also motivated by scalar fields. So these are broadly the motivations for which we can observe the gravitational collapse of scalar fields. So because to understand the gravitational collapse of scalar fields, I'll first talk about the general assumptions that I'll be discussing in and around. The line element will be the spherically symmetric general space-time. in this line element, all the functions, all the metric functions like nu, psi, and capital R is again the physical radius of the collapsing cloud. They're all functions of the co-moving radius and coordinate time. And I'll limit myself into the collapse of type 1 matter fields. It is given in the large scale structure. I mean, it was classified by Hawking and Ellis in their book called Large Scale Structure of Space-Time. And it is, the type 1 matter fields are identified by the eigenvectors of the stress energy tensor of the same matter fields. It will have one time-like and three space-like eigenvectors. And then if we align the basis vectors of our co-moving frame along these eigenvectors, we'll have a line element given in the first equation. Then the second assumption is we are always abiding by weak energy condition. So any co-moving observer or any physical observer will observe the energy density to be always positive, and the sum of the energy density and the pressure along any of these three directions, I mean by r, theta, and phi, along all of these directions, the sum of the energy density and the pressure will always be greater than equal to 0. And also, I'll assume the equation of state, which is the linear proportionality constant between the pressure and the energy density, to be a function of both co-moving radius and the coordinate time. And mostly in most cosmological scenarios, omega, or the equation of state, is always assumed to be a constant, but there is a lot of literature where this equation of state is a variable of both R and T. So now I'll move on to fundamental results of this. I mean, I will move on to the results that I have worked to produce. So the first thing I'll talk about is the visibility of a singularity. There is a comparison between two different scenarios here. In the left panel, I mean my left, there is the diagrammatic picture of how a homogeneous collapsing cloud produces a singularity. It was first seen by Dutt in 1937, and then in 1938, Robert J. Oppenheimer and his PhD student Snyder have shown the same result, that if a homogeneous cloud collapses under its own gravity, it will produce a singularity that is hidden by a event horizon. And this is the collapsing scenario, collapse scenario from where the Schwarzschild black hole actually takes birth. So the left-hand side picture is a diagrammatic picture where we see the birth of a Schwarzschild black hole. You can see, the zigzag line represents the singularity. So you can see that the collapsing cloud makes the singularity at a single point. Is my pointer showing by any chance? This is the point where the singularity occurs. And before the singularity is even produced, there are the horizons starting to form. Okay, so there is no instance where an observer can observe the singularity. But then by Lemaitre, Tolman, and Bondi, where they introduce some inhomogeneity in this collapsing cloud, the horizons, the apparent and event horizon, form at the same instant of the singularity formation. And there is a family of outgoing null geodesics that can escape from a singularity. And there are multiple of papers by Professor Pankaj Joshi and Professor I.H. Dwivedi with, multiple people, including Malakarina and Professor Rituparna Goswami, where they have shown that uh, in multiple cases, if they introduce a very small inhomogeneity into the collapsing cloud or a pressure into the collapsing initial configuration, then the singularity is to visible to either an observer who is close by or an observer who is distant. Yeah. So I'll first define what a singularity is. It is okay. So if we have inextendable geodesics in the manifold, and if at least one of them is incomplete, then we say that the manifold has a boundary, and the boundary of the manifold is itself the singularity. So within the manifold structure of GR, we cannot actually say what a behavior of the singularity will be like. We can only say the limiting behavior of the singularity. Then to define whether the visibility of the singularity, we'll see what will be the behavior of the outgoing null geodesics very close to the singularity. So for that, we will define the expansion scalar of the outgoing null congruence, which is just the covariant derivative of the outgoing null geodesics, which is given in the first equation. It is given by theta L. So nabla I k I is the outgoing null the expansion scalar of the outgoing null congruence. And when the outgoing null congruence has a positive expansion scalar, then the singularity is at least locally naked. It means that, uh, let's say we have a point light source and there are multiple null geodesics escaping from the source. It should happen that the wavefront, which is in this case a spherical wavefront, the radius of the wavefront should always be increasing. But if it is very close to a singularity, the wavefront might not be increasing in radius at a later time. It might also be decreasing. In that case, there will be uh, trapped surfaces where the expansion scalar will be less than 0. And the critical boundary between these two regions, where theta L is less than 0 and theta L is greater than 0, will have theta L exactly equal to 0, and we'll call it the apparent horizon. Okay. So the apparent horizon will give us a local description whether there is a region of trapped surfaces surrounding the singularity. If the apparent horizon does not occur at all, we can say that there will be family of outgoing null geodesics that escapes from the very close to the singularity and reaches some external observer, external asymptotic observer. And then uh, it was postulated by Kepler and then later showed by Clark and Krolak that for a singularity to be physically viable, the singularity should crush any approaching object to a volume 0. And they said that the Jacobi volume is defined by the wedge product of the geodesic deviation. Okay, let me rephrase. Yeah, so we'll have time-like geodesics that end up in the singularity in future. And in this case, we'll have geodesic deviation equations for all this focusing time-like geodesics. And the solutions to the geodesic deviation equation is called Jacobi vectors. And by the wedge product, we define wedge product of the Jacobi vectors, we define the volume element that is approaching the singularity. In neighborhood of the singularity, if this volume element goes to 0, then we can physically say that any object that is approaching the singularity will be crushed to zero volume, and then the singularity will be strong. And Clark and Krolak actually showed that the Ricci tensor, uh, the projection of the Ricci tensor along the directions of time-like congruence Ki and Kj will give us the third equation, and we'll take the affine parameter. We have to take the affine parameter approaching zero. It can never actually go to zero because we cannot actually reach the singularity in a manifold structure. Then I'll talk about the results of the paper that I have written with Professor Joshi, Karim Mosani, Tapobroto Bhanjo, Jay Trivedi. Okay, so here we compare three different pictures. First of them is a specially homogeneous perfect fluid, and it is characterized by the equation of state parameter omega A. And there is a specially homogeneous scalar field, and the potential in this case is not zero, and also a specially homogeneous vector field, which is characterized by its field strength A tilde. And in this case, we have shown that the equation of state parameter, which is a variable function of the scale factor A, will only say whether the singularity is visible or not in case we have an unhindered gravitational collapse. So in this case, the dynamics will be dictated by the Friedman-Lemaitre-Robertson-Walker line element, which is given in the first equation. We have only taken the flat FLRW metric. We could have also checked it for closed or an open FLRW metric, but we started at this. And in our scheme, the stress energy tensor is given in the second equation. And the equation of state parameter, as I have already said, will be a variable function of the scale factor. And in this case, we found out that if the equation of state parameter follows the first equation, then there will be no trapped surfaces. So, and the singularity in this case will be globally naked, because if there is no trapped surfaces, and we are talking about a homogeneous collapse here, so the singularity forms at a single instant in the coordinate time, and at the very same time, there is no occurrence of any horizon. So it can also never occur in the future. So the singularity will be present and there will be no trapped surfaces outside the singularity. Hence, the singularity will be always visible. So it will be globally visible. And the singularity will also be strong if the second equation is true. And there will also be a non-zero subset of equation of state parameter omega A. If it is within the range given in the third equation, the singularity will be both visible and strong. So in this scheme, we have generalized past results. The unhindered gravitational collapse of scalar field have been shown by various other people like Christodoulou, Goswami, and many other people. So in this case, we have generalized this result, and using this scheme, we have plotted these two results where we see that a massless scalar field in which Bs is zero, of course, then the red line shows the singularity, and you can see that in the case of a massless scalar field, the singularity forms, and even before the formation of the singularity, the horizons, both of the horizons, like event horizon and apparent horizon, form. So the singularity is never visible from outside. But as it can be seen from the second picture, if the potential is given by the exponential of phi, that is the scalar field function, then the singularity forms and the apparent horizon and the event horizon never form. So in this case, the singularity will be visible for asymptotic observers. So this was our result. And then I've told you in the first that there is a very, fascinating thing called the critical phenomena of massless scalar fields collapse. So in 1993, Chopwick has shown in a numerical work that if there is a family of massless scalar fields and they undergo a gravitational collapse, then there will be a single parameter family, and depending on a critical value of that parameter, the scalar field will either end up in a black hole or it will disperse. I mean, the collapse will start, and for very specific values of the single parameter, of one single parameter, the collapse will end up either in a black hole or in a dispersal. Okay, and the mass of the black hole is given by the first equation in this slide. Here, P is the single parameter family, and P star is the critical value of that same parameter. And there is a power law dependence, power law relationship between the mass of the black hole and these parameters. Chopwick has also seen that the value of this exponent is universal, and this P star is an attractor in the phase space of this parameter P. So you can see from the equation itself that if P falls very close to P star, then the mass of black hole will be arbitrarily small, or in his paper, actually, Chopwick says it will be a zero mass black hole. He has also shown that this solution shows cell similarity. By cell similarity, I mean that the scales of the combing radius and the coordinate time does not matter in this case. It will be scale independent. This phenomena will be scale independent. But it so happens that Chopwick has picked out very specific scalar field functional families and shown for them that this kind of a phenomena occurs. And he has also not shown it analytically. And there have been numerical attempts. Many other people has confirmed this result shown by Chopwick, but there exists no analytical proof to this. So in an ongoing work, which is under preparation now, we have also actually find out an analytical result where we can see that we have seen that the massless scalar field, if it undergoes an unhindered gravitational collapse, then this kind of a phenomena can be seen in all scalar field families. I mean, all massless scalar field families. There will also be existing a dimensionless parameter which will decide whether whether the end state will be a singular state or it will be a regular end state. In this case, we have also seen that the scalar field is necessarily of type 1, as described by Hawking and Ellis. And we have observed 4 different outcomes in this scenario. I mean, the unhindered gravitational collapse of massless scalar fields. If this single parameter family, scalar field family, has a parameter not close enough to the critical parameter, then there will be a dispersal and the end state will be regular. And it can so happen if the critical parameter, I mean the single parameter falls very close to the critical parameter, then we can observe a zero mass black hole, and there will also be a zero mass locally naked singularity. And in the later case, we have also find out that for a different case, we will have a black hole with a non-zero mass. Now I will move on to the applications in cosmology of scalar field collapse. So I'll first talk about how a scalar field can reach a stable equilibrium. By stable equilibrium, I mean regular end-state stable equilibrium. The stable equilibrium requires that the physical radius will be decreasing, but at an asymptotic coordinate time, the first order derivative of the physical radius and the second order derivative of the time derivative of the physical radius will go to 0. And in this case, we'll also observe, I mean, we have to observe that the first and second order time derivative of the scale factor will actually go to 0, which is shown in the first and second equation in this slide. But if we do not have the relationship between the scale factor and the coordinate time, we cannot actually observe these two equations. So the third equation actually represents what will happen if we have a monotonically decreasing function of co-moving time A, which is the scale factor of the collapsing cloud. In this case, at any time later than the equilibrium condition, all the higher order derivatives of the scale factor, that is A dot, A double dot, and all these, oh, sorry. Okay, sorry. Yeah. So if we have to achieve an equilibrium end state, then all higher derivatives, all higher order time derivatives of the scale factor will actually have to go to 0 at any later time than T equilibrium. So, again, I have not written it here, but we have seen from the first results that I have shown you that if we take a flat FLRW metric, it is not possible for us to achieve a non-singular or regular end state. So we have to have a closed or an open FLRW universe to end up in a equilibrium solution. We have taken a closed FLRW metric because we know that the universe with matter in it will be represented by a closed universe, closed FLRW universe. We have taken a closed FLRW line element here. And then starting from this, we have found out the potential functions of a associated to a scalar field that will lead us up to an equilibrium solution. So in this case, we will have two independent, actually we'll have three equations. One will be the Klein-Gordon equation corresponding to the scalar field, and the rest of the two equations will be the FLRW equations or the Einstein equations for this particular scalar field. But these three will not be independent and will end up with two independent PDs here. And then we have three unknowns. The first unknown is the scalar field itself as a function of the scale factor. The second unknown function is the potential associated to the scalar field. And then also we don't know how the scalar field, scale factor behaves with time as well. So we have exploited the freedom in this scenario, and we have chosen that the scale factor should look like the third equation, the last equation here. So for a collapse to occur, as I've discussed before, the A dot sorry, the first order time derivative of the scale factor should be negative, and in this case, the beta or the constant coefficient of this function should be negative. And then if FA asymptotically reaches FAE, then we'll have 0 here, and A dot will asymptotically go to 0. I mean, the first derivative of the scale factor will asymptotically go to 0, and then we'll achieve a stable equilibrium. And then we have actually used Fade-Bruno's partial derivatives, scheme of partial derivatives, and achieved a bound on this free parameter alpha, and found it to be greater than or equal to 1. And then for alpha greater than equal to 1, if we take the scale factor very close to be the scale factor at the equilibrium, then we have found out that the potential will look like the third equation in this slide. Okay, so we have found out what will be the equilibrium end states occurring from a collapse of homogeneous scalar fields. Now, we should also think about what are the potential, what are the potential uses of this same study. So in this slide, you can see the plot of the sky coordinates versus the density distributions of galaxies. It is taken from the SDSS sky survey. And you can see there are a lot of accumulation of mass around the red dots. So the universe is more or less homogeneous, but there are large scale structures, and we do not actually know how these structures came to picture. We have used the results from the last section to comment on this problem, this open problem. So to comment on the large scale structure, we have seen going through the existing literature that the large scale structure studies actually perturb the linear gravity regime. And then by perturbing the linear gravity regime, they try to comment on what will be the potential functions that could lead up to formation of large scale structures. In this, in this scheme, a very popular prescription is the top hat prescription. It is called top hat because the background is flat. Because the background space-time is flat, and on top of the flat space-time, wherever we have structure, they assume that the structure will also be homogeneous, and it looks like a top hat. So with matter, the potential will just be shifted by some linear value, and without mass, it will look like just a top hat. And they assume that the overdense sub-universe will be, okay. Then they assume that the overdense sub-universe will be governed by pressureless dust in closed FLRW geometry. And there will be two phases in this collapse study because at first, both the background and the overdense sub-universe will have to expand. At some point of time, they should reach a halt, and then it will collapse on itself and produce the regular stable structure, which will be called the structures, large scale structures. And the halting of the collapse is prescribed by Newtonian virialization in the classical top hat prescription. And why is our approach novel here? Because we haven't used any kind of perturbation in our own study. It is completely general relativistic. Then in the large-scale structure studies, classical large-scale structure studies, the potential functions is presumed to begin with. We haven't presumed any kind of potential functions. And then we also haven't used Newtonian visualization to stop this collapse or halt this collapse. And another important point to note here is that in general relativity, there is no counterpart to Newtonian visualization. There have been multiple attempts, and there is no prescription to relativistic relativistic visualization. So in our case, we haven't used visualization to halt the collapse, and we have seen that it stops at an asymptotic co-moving time. Then we come to the dynamical description of the overdense subuniverse, which is first expanding. So first, the equation 1 shows that the scale factor will be related to the physical radius of the collapsing cloud. And at the initial phase, the cloud will be expanding. And in this case, the velocity of the shells of the cloud will be positive because it is expanding. But it will expand in a decelerating rate. Hence, the double derivative of the scale factor will be negative. And at some point of time, the cloud will first halt, and at this point, the velocity will be equal to 0, but it still has to collapse. So the acceleration will still be less than 0. And in the collapsing phase, both of these first and second order derivatives will be negative. And at some later point, at the equilibrium configuration, it has to halt. Using this scheme, we have actually used the results of our previous work to show that it will halt. And then comes the next question. What will be the description of the expanding phase of this overdense subuniverse? So the geometric description, we haven't presumed what will be the line element of this expanding cloud. So we have kept it open and taken it to be the spherically symmetric line element. And because we're talking about the stress energy tensor of a expanding cloud, which has both matter and some scalar field, the stress energy tensor will have contributions from both of these components. So in this case, the T mu nu dm represents dark matter, which we have assumed to be ordinary pressureless dust. And the T mu nu phi is contributed from the scalar field, which we have assumed will be given by the scalar field. In this case, we also, we assume that it will be contribution from the dark energy sector. And we haven't assumed what will be the functions phi and d phi. And then it will be an isotropic fluid. So the pressure along each of r, theta, and phi directions will be non-zero and non-vanishing. And the unique components in this case will be given by equation 7. Okay, so using the matching condition given by Israel and Darmoa, we have matched these two phases of first expansion and then collapse. We have shown that these two phases match at a specific hyper. Okay, sorry. So we have shown using the matching conditions that these collapsing phase and the expanding phase actually match at a space-like hypersurface. And then we have shown that in the expanding phase, the closed subuniverse will be governed by dust, pressureless dust, and the pressure in this case will be 0. And in the collapsing phase, the contribution from the dark energy sector will be increasing, and only by the contribution from the dark energy sector or the scalar field, the collapse will halt and produce a regular end state, which will be the structure in the universe. And the potential class that we have found out to stop the collapse is tachyonic in nature. In this case, when I mentioned that the potential will be tachyonic, the mass or the effective mass of a tachyonic potential is shown to be in the literature to be imaginary. But then we have calculated the Misner-Sharpe mass function or the geometrical mass for this specific scalar field potential, and it will always be real and positive for a closed FLRW spacetime. And those are the results. I thank all my collaborators who are my guide, Pankaj Joshi, my very good friend, Dr. Karim Mosani, Professor Rituparna Goswami, Dipanjanda, Jay, and Tapobrata Da. Thank you very much for listening. And if you have questions, please.
Thank you very much for your very interesting talk. And now we have time for questions. Okay.
Yeah, I have a question about the.
Yes.
So in the middle, I think around slide 15, you had the
Yes, sir.
next singularity.
Just let me go to slide 15. Yes.
I think earlier, a bit earlier. So the before this slide. So
this.
Yes, and I think 2 slides before. So you had the possibility. Yes. So this is Friedman Robertson Walker. Yes. So
yes.
What is the space-time? So in the next slide, you have this next singularity.
Yes.
So what is the space-time? So is it this Oppenheimer-Snyder, or it's so what kind of space-time it is? So is it...
Okay. So yeah. So I haven't given the complete mathematical description. So in this case, there is a FLRW, flat FLRW space-time, and we have matched it to a generalized Vaidya space-time outside. Okay. So as you know that the FLRW space-time produces a singularity everywhere. So to summarize, the whole FLRW space-time will collapse to a singularity, and the rest of the space-time will be governed by the generalized Vaidya space-time only.
Okay. Thank you. You go.
Yeah. So do you? I mean, could I clear myself, or should I?
Yes. So now I know. No. So the only one additional question is, what is the equation of state of this dust, not dust, the scalar field inside? So you just solve the exact Klein-Gordon equation, or you just making this fixed omega or something like that? So how are you solving this?
In this case?
Yes.
Yes. So the equation of state parameter is variable. It is a function of the scale factor. We haven't assumed equation of state to be any specific function to be precise. And we have seen what will be the bound on the equation of state if we want to have no trapped surfaces, and if you don't want to have a singularity which is gravitationally weak. These two, these two inequations only give us those conditions.
Okay, thank you.
Yeah.
Okay. Further questions, comments, remarks? I can't hear any. So let us thank the speaker again.
Thank you very much.
I thank everyone for participation in this seminar, and we close the meeting.